study at the University of Pittsburgh. I should say the era of levitation is here. Now, while many of you may be thinking flying cars, I do apologize, those days are still a far ways off. However, membranes on the nanoscale are on the brink of overcoming gravity. My project is the development of nanoscale porous membranes for the levitation of micro-electro-mechanical systems, which are also known as MEMS. The physics behind levitation is really quite simple. Now we must ask the questions how, why, and also the broader implications and uses for this technology. The premise behind my research is predicated off of Crookes radiometer. Crookes radiometer was invented by Sir William Crookes in 1873. The easiest way to describe Crookes radiometer is that it is a partially evacuated chamber that contains a mill with 4 wings mounted on a vertical pivot point, as shown over here. One of the surfaces on each mill is coated to absorb photons and is black, and the other side is made to reflect photons and is of silver or a substance of the light. When Crookes radiometer is placed in bright light, as it is shown over here, it spins in rough correlation to the intensity of the light. The more intense the light, the faster it spins at the edge of a surface, and in our case, at the edge of the surface, and as shown over here, this is a cross-section of a vein. You have your black section that absorbs photons, your white section which reflects photons, and contrary to like a radiometer, is that it doesn't actually need a motor, and you get these gas kinetic forces as long as you have it within one mean free path of the edge of a surface. And the problem that my research set out to address is how to maximize and use these gas kinetic forces for levitation at atmospheric pressure. As I said, Crookes radiometer works in a partial vacuum. All that it takes to levitate a membrane is you need more force than there's gravity. So let's pretend that this red card is a vein of Crookes radiometer. So you have the edge effect on the side, and you're getting the forces just around the edge. So we have to increase the edge to increase the forces. So one method is you can merely increase the size of the vein. However, yes, you have indeed increased the amount of force, but you've also increased the surface area and have increased the weight, and we want to minimize the weight. So another method that we can do to increase the edge effect, pretend this is a hole puncher, which it is, and you start punching holes into your membrane. And this actually solves 2 problems for us, because now you have a membrane that has a lot of edges, because you have the inside of the circles, and you've also taken out a lot of the weight. You decrease the weight, increase the forces, and it just makes it easier for something to levitate. So this is what my membrane looks like. The red parts are approximately 70 nanometers across, and this is because the gas kinetic forces only work at one mean free path, which is 70 nanometers. So we want to create this membrane with a lot of holes in it. But the problem when you create a membrane with many, many holes is that it becomes extremely fragile. So then once you have these holes, you also have to, this green part acts as a scaffold to kind of hold the tiny membranes in place. And that is what my research set out to address, is how to actually create one of these membranes where you have a lot of gas kinetic forces, a lot of holes, so that this membrane will levitate. And this is a visual my professor used in SEM. And so you have a scaffold over here, and then inside these holes are these little tiny membranes, these little circles where the gas kinetic forces are going to act. So a lot of research has been done onto how to actually create these tiny and so the actual process of creating these pores is done via an anodization process, where we take that aluminum substrate and we put it into this jig configuration over here, where we pour oxalic acid on it and we put it at 40 volts at approximately 20 milliamps, and we let it run for about 15 hours. And we end up with, this is another SEM picture from our professor, but this is what the pores actually look like. You end up with a lot of pores, and the top part of the pores, via the process, are open, but the problem is the part that's touching the aluminum, which is over here, all the pores are closed. And as long as the pores are closed, you actually end up with no gas kinetic forces, because you can't actually get any molecules flowing through these nanopores. And that's part of the problem that my research was addressing, is how do you actually remove these pores from this thick aluminum plate that we've made and open up these pores so that these gas kinetic forces can work. And in order to, the next step that we have to do is we already have the pores. And we're throwing this scaffold on top of our oxide, which is this blue layer. So we etch it with a laser, and then we use acids, and then we strip the photoresist, and we acid in hydrogen peroxide. And at the end of the day, you basically end up with your scaffold on top of your little tiny membranes that are going to generate these gas kinetic forces. And you have your aluminum substrate on the bottom. And then there's a hard process of how do you actually remove the membrane from the aluminum disc on the bottom. And this is the part that I did not complete with my research, and I would recommend to the Space Grant Consortium to extend the summer research program another 2 or 3 weeks. But just as a reminder, you end up with an SEM picture like this. You have your scaffold and your tiny pores, and we have to open up these pores so that gas kinetic forces can work, and you have these forces. And so there's a couple methods that we can use to actually remove this coating of oxide that has these pores from the aluminum substrate. And so one process that we have is we can reverse anodize the sample. That's where you apply a negative current to it. And what happens is this oxide coating actually kind of falls off this aluminum. But we found that it actually is a very delicate process because kind of think of these pores as very, very thin nanotubes of glass. And they're extremely, extremely fragile. And it's using copper sulfate with a mixture of hydrogen chloride. And this research, at the time I made this, it actually has been done in the past 2 days. And we end up with the copper sulfate actually covering all the nanopores that we want to operate. So it's just another unfortunate event happening trying to get this membrane off. So once you actually get the membrane off, remember when we made these pores, they're just 40 nanometers by 100 nanometers, and we need them to be 70 nanometers so they work on the mean free path of gas, which is approximately 70 nanometers. So we have to cut the pores a little to shorten them from 100 nanometers to 70 nanometers. And we do that using argon plasma etching or using phosphoric acid. And then after that, we then open the pore diameter from 48 nanometers to 70 nanometers using phosphoric acid. You can't do them at the same time because then you end up over-expanding or under-expanding, and it's not so good. So the question really becomes, actually, what do you do with a membrane that can levitate? And I have no questions this membrane will levitate in a couple of weeks. But so the reason why this membrane is going to levitate, let's take this piece of paper, pretend it's a membrane with holes in it. It basically generates this airflow around it. So when you heat up the bottom side with a laser, just like you would Crookes radiometer, you end up with these forces acting down, and your membrane will take off. So just like, so you have the application of it flying, but then let's say processors these days in your computer are approximately 35 nanometers. So if we take a membrane and put it on top of your processor, but don't let it move, then you get air circulation around your membrane over the processor. So you eliminate the need for a fan, and this has a lot of energy-saving applications. After that, then there's also, you can possibly use these to generate, like I said, these air currents around it. So say you put some contraption to capture these air currents, say like a little tiny windmill of sorts, you can then capture that energy. We can use this to levitate micro-electromechanical systems, which is really cool. You can kind of have them in the upper atmosphere. Say you have the sun beating down, and it'll just kind of continuously just sit in the upper atmosphere for many years. And then also, levitating things is really, really cool. And it's awesome to say that Prince Ali from Aladdin from our summer research. I'd like to say some quick thank yous to the NASA or the Pennsylvania Space Grant Consortium. Dr. Brian Durso was my project advisor. Unfortunately, he was ill and could not make it. And to Elliot Jenner, who's a graduate student. And unfortunately, he also cannot make it due to his committee meeting that's currently going on right now. So if we could all say a short prayer for him, that'd be much appreciated. Thank you so much. Let's hear the questions.